So Brajesh, there is, I think there are a couple of questions in the chat.
Yeah, sure. Okay. So yeah, a couple of questions. Do you have real machine noise models we can load into the noisy simulator? So I mean the real, as you can imagine, you know, simulating the noise of a real machine is quite difficult. So I mean they are not available, just for you to run, but you can bring your own noise model, to run on these machines. So and do you have a pulse simulator? Is it offline or online? If you go to these devices, um, look at, okay, it's right now available. I'm going to show you. Yeah. So for instance, if you look at the Rigetti device up here, uh, there is a pulse control. It's supported here for these devices. So if you run the code on your device on Rigetti, you can take advantage of the pulse control as well. Okay, perfect. All right, so let's take this time to check back on the QPU task, if it's already completed. So we can run this again and see what the result is going to be. It looks like it has been completed. So we can look at quantum task. Oh, it is still queued. So that just means that we have to wait for some more time. Okay, so now we can go ahead with the second part of the talk today, unless there are many more questions up here. Okay, all right, so I'll take that as a no. And now let's talk about a feature called Amazon Braket Hybrid Jobs. So, okay, so at the moment, I mean, all the algorithms that are classical quantum algorithms, in the sense that the quantum computer and the classical computer work in tandem with each other, right? This is very similar to what happens with GPUs. For example, on this diagram up here, when you train a neural network, what you do is like you update weights on CPU, and the new weights are given to to the neural network, and the neural network basically runs on GPUs and calculates the error value, batch error value, and then that is used to compute the objective function that is again used to update the weight, and this cycle goes on and on, right? In the same way as you would do with the neural network, what you do is you do with the quantum circuits. And the idea is that these quantum circuits, the gates have certain parameters which play the role of the weights in a neural network, right? So in this diagram up here, what you do is CPUs are used to update the variational parameters of the circuit. New parameters are fed to the quantum circuit, and that quantum circuit is ported to QPUs, for execution, and the result is used to compute the objective function and then update the variation parameter, and then this cycle goes on and on, right? So in this way, the algorithms which use this kind of arrangement of constant exchange of information between classical and quantum computer are called hybrid classical quantum algorithms, right? And at this moment, like since the quantum devices that we have are limited in the capacity, and in their quality, hybrid classical quantum algorithms are our best bet, to explore the or any potential quantum advantage, right? And if you think about it, in some sense, even if we have the full-fledged quantum computer with fault tolerance and error correction, in some sense, the paradigm is still going to be a hybrid model, right? Because the quantum computer are not expected to completely replace classical computers, but work in tandem with each other, right? The classical computers CPUs or GPUs will still be used in some capacity for pre and post processing, right? Now, so how you can implement hybrid algorithms with Amazon Braket? Basically in 3 different ways, right? First is basically you have access to Amazon Braket SDK, and you write your own hybrid algorithms where you define what part of your algorithm or script is going to run on CPU, what other part is going to run on GPUs or simulators, right? And for this, there are growing lists of examples available through Amazon Braket SDK development, documentation webpage. Then there is PennyLane. So PennyLane is a Python library that is quite well developed, and it has quite a big of user base, and that is compatible with Amazon Braket hybrid jobs. So PennyLane, basically using PennyLane, you can define these hybrid algorithms, that uses classical and classical and quantum computing resources. And since PennyLane is compatible with Amazon Braket hybrid jobs, you can directly run that code on Amazon Braket as well. Then there is a feature called Amazon Braket hybrid jobs or Braket hybrid jobs, using which you can create hybrid jobs there as well. The advantage of using Braket hybrid jobs is that one has priority access to QPUs, right? For instance, let's say you want to run a parameterized quantum circuit that has multiple iterations. So multiple iterations means that you need to submit many quantum tasks in an array, in a row. So for that, if you use Braket hybrid jobs, you would not need to wait in the queue for every time you submit the job, but you can submit that as a batch. So in that sense, you have priority access to QPUs, right? So there are several ways for you to implement hybrid algorithms with Amazon Braket. Let me take a look at the questions up here. Okay, so that's all good. So are there any other questions before I go ahead? All right, so I'll take that as a no. So let's quickly revisit several level of execution of quantum circuit. So first we looked at shots. So one shot is basically a single execution of a quantum operation on a device. Then there is a task. So a quantum task can comprise of multiple number of shots. So when we ran the quantum circuit on simulators and we defined shots equal to 1,000, that was one quantum task with 1,000 shots. In hybrid jobs, what one can do is you can apply a sequence of classical and quantum compute cycles, and in each cycle, you can implement thousands of tasks in each job, right? So that's increasing a level of engagement of running a quantum circuit. Multiple shots make one quantum task, and multiple quantum tasks can be included in one hybrid job, right? So at a glance, basically when you look at hybrid jobs, this feature, what you do is basically as a user, you will see that there is a job instance, basically. So that job instance is actually defines the distribution of what part of job your script is going to run on classical resources, what part is going to use the on-demand simulators, and what part is going to use the actual QPUs, right? And then this cycle goes on, and that's what basically quantum hybrid jobs is. So in a way, you're combining the classical and quantum compute resources in an efficient way, to optimize on performance for on these NIST era of devices. With hybrid jobs, what also is that you can take advantage of monitoring services such as CloudWatch and so on and so forth to look at the almost real-time progress of jobs and metrics, right? So the architecture of hybrid job looks something like this, right? For example, you have a job instance that works with managed simulators and that interacts with quantum hardware inside Amazon Braket. And then it interacts with CloudWatch, basically, that can be used for monitoring, storage of results, uses Amazon S3. And then there is Amazon ECR, right? So the idea here is that when you run Amazon Braket hybrid jobs, what you can do is you can containerize the entire algorithm, right? So there are three different kind of containers already provided for you. And one is basic container. There's one based on PyTorch, and there's one based on TensorFlow. So there are three containers that you can utilize basically to build or run your favorite hybrid job or hybrid algorithm. What you can also do is you can bring your own container, right? Let's say, for example, in your machine learning pipeline, you need a particular package that is not available in any of these already provided containers. Then you can bring your own container, build your own container, and register that container using what is called Amazon Elastic Container Registry. And once you register, you can use that container all the same, right? So that's one of the features that you can utilize at Amazon Hybrid Jobs. So let's use the information that we have just gathered about hybrid jobs to solve an optimization problem of what is called quantum approximate optimization algorithm. Before I go ahead, let me take a quick peek at the chat. Are there any questions? Okay, so it seems everything is happy and healthy up here. Okay, so let's look at the optimization problem with the QAOA. So the optimization problems are ubiquitous. I mean, you see them everywhere. Like, for example, in manufacturing, logistics, finance, and all sorts of fields, right? So any attempt towards solving these kind of optimization problems is going to be useful in many areas of application. One particular problem that is quite interesting is called the max cut problem. So the max cut problem is it's an NP-hard problem, right? And all that means for the purpose of this talk is that when you increase the size of this graph, then finding max cut, which I will tell you in a minute what it is, finding max cut becomes exponentially more and more hard, like exponentially harder if you increase the size of the graph, right? So let's look at what is max cut problem. So the max cut problem basically is that given a graph, what we want to find out is that a partition of vertices in two subsets in such a way that the number of edges between these two subsets is maximized. Okay, so for instance, if we have this graph, right? And if you partition this graph into two sets, like one orange, where there are like this node, and this node, and one red, which contains this node and this node, then there's if we like partition this, like then there between this set, red and orange, there is 1, 2, 3, 4, and 5 edges. So that is a max cut solution. So the max cut solution to this graph would be partitioning between two subsets, where one subset contains the red dots and the other contains the orange one. Okay. For a simple problem, a simple graph like this, it's very trivial. It looks very trivial, but when there are like the graph is quite large and everything, then it becomes quite hard to solve this problem. Okay. Any question about max cut formulation? Okay, nice. So in a classical, classical algorithm, the way you can formulate this Maxwell problem as an optimization problem in the following way, right? So if you're familiar with optimization problem, what one is trying to do in optimization is just trying to find out either maximum or minimum of an objective function, right? And this max cut is basically what? Max cut problem is basically trying to find the maximum number of edges between two subsets. So that's all we do. We defined an objective function up here that basically computes the number of edges between two subsets, right? So one can define it in this way. This function, like max of half of 1 minus si sj, where si and sj can be either -1 or +1. And we just try to maximize this function up here, which will give us, the sets of a string of samples with either -1 or 1, basically, which will, maximize this objective function, right? So, for instance,
I'm sorry. Can you bring a solution that is not optimal? Just to understand better the problem. I'm not understanding very well. So if you can give examples of 3 solutions and then the optimal, that will help.
Right. So I will. Right. I was going to do the next exactly that. So this is the optimal solution, right? If we were to get a suboptimal solution, let's say we cut this graph in this way, where these 2 edges are in one subset and these 2 edges are in another subset, right? So the number of edges between this subset and this subset is just 2, 1 and 2, right? So that will be a cut where the edges are 2.
Yeah, if sorry. So edges are the lines?
Yeah, the lines. The edges are the lines connecting between these different vertices.
Okay.
So
if you do the vertical cut.
If vertical cut, that cuts 2 of the lines. So there are 2 cuts, right? If I do a partition in such a way that the lower 2 are in one subset and the upper 3 are there, so I partition it in this way, then this is 1, 2, 3. 3 cuts are there.
Okay.
Right? But if I do partition in such a way that I do a cut starting like this and like this, right? Then this cut has 1, 2, 3, 4, 5 cuts. So that is a max cut solution.
Okay, good.
Okay, so that's how it is. Yeah. So this objective function, it has been shown to act as an objective function to find the solution for max cut problem as an optimization problem. Okay. So the classical formulation looks as this, where S basically is Si and Sj are they label the vertices whether they are in subset -1 or subset 1, right? So for quantum formulation, what one can do is promote these Si and Sj to these Pauli operators sigma z, which has eigenvalues -1 and 1, right? And what one at the end, what one is looking for is a state. So this is the Hamiltonian. This is a Hamiltonian function that is equivalent to this objective function, the classical objective function. And all we need to do at the moment, now, is find the maximum eigenvalue of this Hamiltonian up here. Okay, and I can state that maximizes the eigenvalue of this Hamiltonian, and that is what we need to do. So the way we do it in this is that, again, we take the analogy of quantum neural network. So for instance, in this QAOA circuit, so for the purpose of this talk, I have just treat this QAOA as a black box, right? As a black box where we have like initial bit of register, like qubit register, And then there are like some parameterized gates, just as there are like parameterized weights in a classical neural network. And then there is some output. So the idea is that these gates, they work on this initial qubit, and when we measure at the end, we measure the expectation value of this operator Hamiltonian HC. Okay, so I don't want to go too much into detail of the mathematics of this, because that is not really necessary, and that will require a completely assessing on its own. But the takeaway point is basically that we build multiple parameterized layers, right? There's like 1 layer, 2 layer, you can have 3 layer or 4 layers as well. And each layer has some parameters, like here gamma 1 and beta 1, which are basically the angles, rotation angles. And what we are trying to do now is trying to find the optimal value of these parameters, gamma and beta, in such a way that the expectation value of this Hamiltonian HC is maximized, right? So if the Hamiltonian expectation value of the Hamiltonian is maximized, that means the classical objective function corresponding to that is maximized, and that means one is leaning towards finding the maximum cut problem, the solution to the max cut problem. So that's all one is doing. Okay, so here, if you remember the classical machine learning pipeline, you have some certain hyperparameters, right? So here a hyperparameter will be number of layers, like layer 1 and layer 2. That will be a hyperparameter. And the parameters, similar to the weights of the neural network, are basically these parameters: gamma 1, beta 1, gamma 2, beta 2, and so on and so forth. So now we're going to use these hyperparameters and these parameters to run an iterative algorithm and find out what the optimal value of these parameters are to maximize HC. Okay. Now, the idea here is that, of course, these quantum devices that we have available, all they do is just run the quantum circuit and give you some result at the output. They themselves do not work as an optimizer. So in this example, what we'll be doing is, for the optimizer, we'll be using classical optimizers, such as your favorite gradient descent method, or so on and so forth. But to compute the value of the objective function, we will be using quantum devices. Okay, right. So let's things will become a little bit more clear when we look at the hands-on lab, which we are going to do right now. So for that, okay, before I go ahead, like, are there any questions that I can answer? Okay, I'll take that as a no. So if we go back to our Jupyter Lab and go to the home page of Jupyter Lab, click on Braket Workshop, Immersion Days, and not in Quantum Tasks, but in Immersion Days, there's QAOA. And if you click on QAOA Penny Lane Hybrid Jobs, okay, I think I just need to refresh this. Days QAOA. Not encoded.
I'm getting the same error.
Yeah. Oh, okay. So this is a zip file, of course. I was not looking at that. So to do this, what we need to do is, yeah, we click in here. Oh, sorry, not here. Yeah. So click on this plus sign up here, and then open terminal. Click on the terminal, and what we need to basically do is unzip this file. So in this terminal, we are here. Go to SageMaker. And in there, we will find Braket workshop. Is everyone with me so far?
Yeah.
Yeah. Okay. So so we need to open the terminal. For that, you need to click on this plus sign up here. That will open the terminal, and then we are going to that directory. Go to immersion days. Then we go to QAOA, and up here we have QAOA penny .zip file. So here we need to unzip this. So we just do unzip QAA -d. You can just write QAA hybrid jobs as the name of the directory. Enter that, and it will inflate. And if you go back to, sorry, Braket workshops, immersion days, QAOA, there is a directory called QAOA penny hybrid jobs. Is everyone able to follow this so far? Works to unzip. Yeah, perfect. Now we click on this, double click on this directory, and we have this QAOA penny underscore hybrid jobs.ipynb, right? Okay, now double click on that, and then voila, we have the notebook. Okay. So in this notebook, now we are going to solve the max cut problem using Braket hybrid jobs. So, and I encourage you to take some time to read through this. Right, it's quite interesting. But in the interest of time, I will go ahead and explain you the hybrid jobs feature and solve this problem. So there are some general imports. We are importing network X package to settle the problem. So now let's just take a look at an example of, a graph with 5 nodes and 6 edges, a graph like this, basically, right? It has 5 nodes and 6 edges. And we want to find out the max cut solution of this. And if you look at this graph, there are multiple solutions of that for this max cut problem, right? So like for instance, you could do a cut something like this, or cut something like this, something like that. So I mean, there are multiple solutions to this this max cut problem, and we will be looking at all the possible solutions up here. So now let's prepare the input initial data. And for
Brajesh,
input
can
initial
I
data,
stop you for there's a comment in the chat. Whether you
sure.
can have, yeah.
Instruction to unzip, right? So go to terminal after SageMaker directory. So if you go to SageMaker, right, and then cd to Braket workshops, Braket, and then type W workshop, enter. Are you with me, Tara? And then go to immersion days, cd immersion days. And if you see there are like multiple here, then go to QAOA. Is that okay? Tara, are you able to follow up here? And to unzip this directory, all you need is unzip this whole thing -d. Let me put this in the chat. You can use this command after you are in this QAOA directory. All right. I hope you can follow the directions, Tara. I'll go ahead. But if you cannot, please let me know. I will try to guide you again up here. All right. So going back to this notebook that we were working through. So first, to prepare input data, like we need to save this graph in form of a matrix, adjacency matrix. So that's what this one is doing. When you do input file path and write the adjacency list of this graph in terms of an input file path, and that creates a file for you up here. So this file basically encodes what the graph is and what its connectivity is, right? If you're interested in looking at the algorithm script by itself, I mean, there's given up here. If you click here, the script is given up here. For example, you define like the input directory, the output directory, the name of the job, and so on. These are the hyperparameters, basically, environment variables that we will be taking a look at. And then we load the hyperparameters, right? And so on. And at the end, then we are reading the input adjacency file that we have just created, and then finding out how many number of nodes in total there are, and then basically reading the graph, what the graph looks like. And then to set up the QAOA problem, we need to do this, what is called cost Hamiltonian and mixer Hamiltonian. For the simplicity, we are using this as a black box, so I will not go into detail. Basically, these functions can be called by QML. QML is a penny lane. If you look at QML is a penny lane package here, and penny lane package has this built-in cost and mixer Hamiltonian functions for you that depending on the graph, they will give you the exact form of that. And then you build all the layers, like QAOA layers, like layer 1, layer 2, with parameters gamma and alpha, for instance, up here. So that's like the QAOA layer. And then you build a circuit, and then you run this circuit like multiple number of times by defining a cost function. Okay, and this goes on and on for certain number of iterations, and you start the optimization with. In this, one has chosen like stochastic gradient descent method optimizer from the interface, which I will be explaining in a little bit. And then at each step of iteration, we can look at the initial cost and the cost at each iteration. And you can define certain metrics, like for example, the cost function at each iteration, and you can monitor that in real time, as I will show in a little bit. And then at the end, when the iteration completes, and you'll get the value of the final cost function, right? And then you can save the job result in terms of the parameters and the final cost function and so on. Okay, so this is the script, but we are treating the script as a black box for now. So let's not go into too much detail there. The interesting thing now is the job container environment, right? So when you work with, machine learning, classical machine learning, even you need to use many packages and many, different kind of libraries, and it is quite useful to containerize them, right? So here we have 3 different kind of containers already available. Like first is Autograd. Autograd is the default in one, the base container that has penny lane built into it. Then there is TensorFlow, and then there's PyTorch. So you can use either of these containers, which have like basic packages and libraries installed in them. However, if you need something more, you can bring your own container. You can build a container and register them using Elastic Container Registry and use that, right? Now it's a time to configure your job. To configure a job, what we need is an interface, basically what kind of container we are using. So in this example, we are using AutoGrad, right? There is also option of TensorFlow and PyTorch. Now we define the hyperparameters. So hyperparameters basically the number of layers that we are interested in. So we are initially setting that to be 2. Random seed. Seed is basically the seed that is used to generate a graph. Maximum number of simulations in parallel that can be done on a classical resources is 10. Number of iterations, we are limiting that to 20. And each step size in the parameter space is 0.1. And number of shots is 1000. And interface is interface, right? So these are the hyperparameters that we are passing, right? One can play with these hyperparameters, change, and so on. Then we define what kind of device we are going to use. And for this, we have chosen to work with the state vector 1 simulator, right? And then image of the container. So this function select container, basically it when you pass this parameter interface, it selects the image URI of the container that is saved in the Elastic Container Registry of AWS. And that is basically imported as a package, to be included in this hybrid jobs. Okay. Now to submit a hybrid job is quite simple. Basically, you create a job. Basically, AWS Quantum job.create, where you define what kind of device you're interested in using. The source module is QAOA. So basically, the source module is where there's a directory called QAOA where all the algorithm scripts are there. So if you look in here, there's an algorithm script called QAOA algorithm script. So the entry point is just given as that QAOA and algorithm script. And then you pass the hyperparameters and give the path to input data. And then you provide a job name to your QAOA job, right? So this is a descriptive job name. You're free to give any job name, but here we are using interface and time so that every time you create a new job, the job name doesn't conflict with the previous one. Okay, so let's create this job. Oh, so I need to run the previous cell up here, which I have not done. So we run this cell and then we create this job. So it takes a minute to job to be created. And if you click on job state, it is running. So right now the job is running. Now we can go and look at what the health of the job is. So if you go to hybrid jobs, we have a job running up here. We can click on this. It is running right now. And you can see all the information up here, like what is the job name, what device it is using, the source of the script, the hyperparameters that we have passed. It's all updated up here. And what is the input graph it's given. And if you want to monitor the progress, the loading metrics basically. So the metrics are defined as basically the values of the cost function. And it is still loading the metrics, so it may take a minute or so for it to complete. Then you can look at what is called the CloudWatch. So if you click on View in CloudWatch, you can get a lot more information about the status of the job. So in CloudWatch, so basically the job has just started.
I missed that. Where was the Viewing CloudWatch button?
The CloudWatch button is right here. When you look at hybrid jobs, on the right-hand corner, there's Viewing CloudWatch.
Thanks.
Okay. So yeah, so that has not been logged to CloudWatch yet because it takes a minute or so to show up here. And just wait. this code takes like around 7 minutes to complete, 5 to 7 minutes. And if I look at this state of the job, it is still running. So while the job is running, like, are there any questions? I'm sure there is. Like, I gave you a lot of information in such a short period of time. I'm happy to take those questions.
Hi, Brajesh. It's Manolo here.
Yeah.
Is there a way of estimating the cost of a job before submitting it to a real quantum computer?
Yeah. So that's a very good question. So for that, like, we have, some cost tracker available for you. For that, I can just give you the link in here. Cost tracker. Yeah, so there is this article you can look at.
Yep, thanks.
Yeah, and then there is another recent article introducing cost control solution for Amazon Braket. You can go into the details of this. These two are very useful resources that you can look at.
Great. So does that give me the cost for a specific circuit if I'm running it, or a specific job? Or is that just a general?
Yeah, so when you for a specific job that you would be running, it will give you the cost tracker for that.
Great,
And
thank you.
it can tell you the cost control solution. And you can also estimate the cost by, if you know the exact circuit and how many number of times you're going to run it, you can look at Amazon Braket pricing. So here, like, there are like some examples you can look at. For pricing, how the pricing basically is done. So I'll paste this link as well. And there is this pricing page. You can look at, like, for example, if you go to hybrid job tab here, it will tell you like what different kind of storage there is and what the cost of that is. And then there are like examples here, pricing example, like gate-based QPUs, what the price of that would be. Hybrid, let's say you are running a hybrid job in on-demand simulator. So there is an example here, like with 30 iterations and 10 tasks and so on and so forth. This will be the cost. So you can use these examples to, estimate the cost of your hybrid job and task as well. I have pasted the link here as well. Okay.
Great, thanks very much.
Yeah. Yeah. So now see the metrics we can see. So the cost function for this is evolving as this, like at the 6th iteration, the cost function is such as this. So this is what is happening up here. And now if you click on view in CloudWatch, we should see something up here. So, oh, my bad. So in CloudWatch, you see a log stream up here. So if you click here, in CloudWatch, you can see like all the log data, like how the job has started, like training, and all the the environment variable that has been set to certain values. You can see all that, right? Then it says beginning setup, optimization starts, the initial cost function is this, completed iteration 1, and so on and so forth. And at the end, like you can go up to like whatever value is at the moment. So at the moment we have completed 11 iterations. So that should, and we have 20 iterations given. So that will take a little bit more time for it to complete. So if we go back and look at the job state, it is still running. Right. So while the job is still running, are there more questions that I can answer? Like if you look at, for example, when you click on hybrid jobs in the Amazon Braket console, you see there is one hybrid job that is running. You click here, and then if you look at the monitor, so all we're doing is monitoring the cost function, and you see the cost function is going down with some wiggle here. So at 12th iteration, we have cost function is minus 4.428. So 8 more iterations to go. The question is a naive and which puzzles me a bit. Why do we actually need a real quantum device? What does it give us over a simulator which we can simulate using normal CPUs? Is the simulator? That's a good question. So at the moment, I mean, simulators are good because we are trying to simulate a very small device, right? 34 qubits or 50 qubits and so on. But if you want to simulate a device, a quantum device that let's say 100 qubit, that will require huge amount of memory, to be available, a RAM to be available for to simulate that, and that becomes impossible. So a real QPU beyond, like, let's say even 40 something qubits is very difficult. Beyond 50, it becomes almost impossible to simulate even with the biggest supercomputers that we have available. So that's why we need real quantum devices to simulate this, to work with this. Simulators can go only so far.
Okay, thanks. But otherwise, they are equivalent. I mean, within limitations of number of qubits, they would be. There is nothing extra additionally that quantum real device gives over simulator. Is that correct statement or not really?
Yeah, I mean, there are some differences, of course, because the real device has like the real physics built into it. Like real devices are noisy, but simulators are like ideal simulators, right? So that's one difference. And the simulators are using classical resources, and the QPUs are doing like the quantum hardware. So those are also the differences between QPU and CPU, QPU and simulators. But from programmatic perspective, if you look at just like as a programmer, simulator is just another quantum device, right? So that's about it.
Okay, thanks.
I would also mention that not all true quantum computers can do all quantum algorithms. So there's some gate limitations. Whereas ideal qubits, you're assuming it's a full gate-based computer, so you can do all operations, and that's not the case for true quantum computers. So there's that added complexity as well. Right.
So the idea there is like a quantum computer which comes with some native gate set. So to run any general quantum circuit, that quantum gates have to be compiled in terms of the native gates, native available gates. And if the native gate set, the supported native gate set is enough for the quantum algorithm or quantum circuit to run, then you can run those quantum circuit on those quantum devices. That's truly correct. But simulators, like they simulate an ideal quantum device with all available native gate sets, basically, so you can simulate any random quantum circuit.
And for this example, we are running on a simulator of 21 qubits,
right?
Or
that's right.
And
we are using state vectors.
And are we using the full simulator, or how do we know how many qubits we require for this example, for example, or?
Yeah, so you can print out the quantum circuit basically. So that's one way of doing that. And so this is a 2-qubit simulator that we're using. We have 2 qubits. So
we are using the 2-qubit simulator.
Right.
But I'm not completely don't understand what is the load that we are giving to the example, or Yeah, basically the same question I asked. How many qubits do we need for this example?
Yeah, so I mean that is up to so in it's like asking how many nodes in a neural network do you need? So that is up to you. Like you design that neural network, you design that the number of weights and so on and so forth, and then you run that using your available hardware. So this falls into the realm of variational quantum algorithms, where you have a lot of freedom. Like essentially what you want to do is you want to find a quantum circuit. You want to build a quantum circuit with some free parameters, and you want to optimize those parameters in such a way that the value of the objective function is maximized. So you have a lot of freedom in building, in choosing the number of parameters, number of qubits, and so on and so forth. So here we have chosen like 2 qubits to use 2 qubits to do this, and with the 2 layers with the small number of hyperparameters or parameters, the variational parameters, if you will. Of course, you can scale this problem up to larger number of qubits, more parameters. That will give you like a finer, more fine-grained solution. But of course, that will also be more expensive on the simulator. And this is I'm just trying to show you a proof of concept here.
Sure. Okay.
Okay, so let's just check if the job is completed. Okay, nice. The job is completed. Very good. Right. So now we can just look at the job, the result of the job. So it says like the final cost function is minus 4.19 and estimated parameters. So the final converged value of the parameters is as follows. Like this is alpha 1, gamma 1, alpha 2, gamma 2, and so on and so forth. Now you can look at the task summary and all. Now let's go and investigate the results, right? That is an interesting part, and then see whether we have gotten the right result or not. So optimized parameters, basically. So these are the optimized parameters. And now what we need to do is just like neural network, right? When you have the final optimized weights, to get the final result, you need to run the neural network once again with those optimized values of the parameters. So that is what we are going to do now, is that we have these optimized parameters. So we are going to build that quantum circuit again, like using the cost Hamiltonian, mid-set Hamiltonian, and so on and so forth, and use these parameters to run that quantum circuit once again to find out what the final partition of the graph is, right? And that is what is being done here, up here. So we can run this, and this should be fairly short time. Yeah. So now, after running this, what we are seeing here is basically statistics of all the possible outcomes. So here we took like 100,000 shots, and we are estimating what's the probability of observing each of these the samples. And these samples basically represent 0 and 1, basically is the number of cuts. Like if all is 0, all 0 means there is no cut, right? If the 4 are 0 and 1, it means in one subset, the first 4 nodes are there, and in the second subset is the last one. This will become clear in the next slide. Now we can just plot this, and it turns out that there are 4 solutions, like corresponding to 00011, 011100, 10011, and 11100. These have the highest probability of being in the max cut solution. And bear with me for a moment up here. And what we are going to do is now we are going to plot these 4 solutions. So corresponding to this first solution, 00011, this this is the probability. Like we have the partition is such that 0th node, first node, and second node is in red subset, and third and fourth are in the blue subset, right? So basically, what we are doing is like we are cutting this graph in such a way that this all are like this. So the number of cuts here is 1, 2, 3, 4, and 5. So this gives 5 cuts, and that indeed, if you check, that is indeed the max cut solution. You cannot have more than 5 cuts in this graph. In a similar way, bit string 00011, basically this is a symmetric graph, so this is just a complement of this one. So that being said, like 0, 1, and 2 vertex are in the blue zone, a blue subset, and 3 and 4 are in red. So again, this will be a cut like this, and that will give you 5 cuts as well. Similarly, you can have a cut like this, where 1 and 2 are in red, and 0, 3, 4 are in blue. And similarly, just the complement of this one is like 1 and 2 are in blue, and 0, 3, 4 are in red. So there are multiple max cut problems solutions available, and the top 4, the bit string this one has probability 0.1359 and 0.137, 0.138, and 0.139. So what we have done here is we have listed 5 most probable solutions, right? And 4 of these, we see that they are actually indeed a max cut. But the last one, the 5th one has probability 0.03. And as you can see, this is not really the max cut solution, because if I cut it according to this, like 1, 2, 3, 4, only 4 cuts are there. So of course, 4 cuts is not maximum, because we know that there is a bigger cut solution with 5 cuts already available here. So that gives you an idea of like, the maximum probable solutions, the 4 that we see here, they represent max cut. And I see like their lower probability one is indeed not a max cut solution. Okay. So is this more or less clear what we wanted to achieve here? And we have done that using hybrid jobs. Or are there any questions? Okay, so if there are no questions, I mean, this is what I had planned for hybrid jobs so far. And now I would like to go back to the presentation and take like 10-15 minutes to talk about Aquila device. Of course, I don't suppose it will have too much merit to show the hands-on session for Aquila device, but I would like to just give you a flavor of what analog Hamiltonian simulation device looks like. So if there are no more questions, we can go back to the presentation and play from current slide. Yeah, so this device Aquila from QAOA is an analog Hamiltonian simulator, which is different from the gate-based devices actually. It's a QPU technology that is based on neutral atoms that you can program in any like 1D or 2D geometry. And the QAOA Aquila device has 256 qubits, and these qubits are basically 2 energy levels of ground and excited state of a neutral atom, right? And the idea is you can arrange them into any 1D or 2D geometry. So for example, if you have a graph, a 2D graph, then you can arrange these neutral atoms in practically any 2D geometry corresponding to that graph, and try to solve graph-based problems using this device up here. So one of the problems that you can solve is called maximum independent set problem on unit test. So similar to maxcut problem, maximum independent set problem is another hard problem. So the idea is that so maximum independent set problem is as follows. It's basically that you want to, what is an independent set? So independent set is a subset of a graph in which the vertices are not directly connected with each other, right? So for example, in this graph, if you look at these set of these red vertices, none of these red vertices have direct connection with each other, right? So that is an independent set of this graph. And maximum independent set, as its name suggests, you just try to find the maximum size of this independent set, and that is the maximum independent set. It turns out this problem is like exponentially hard when the size of the graph increases. The computation resources required in traditional computing, it grows exponentially. So you can look at these two resources to read more about it. And the idea is that if you want to solve the MIS problem, you can take an adiabatic approach of this programmable, of programmable parameters of the drive field, right? And okay, it seems to be there's a question here. Okay, the question is, why would application? Let me just jump to that. I think, hang on 1 second. Yeah. So unfortunately that slide is not available, but to answer your question, so these kind of devices, they are very, hardware specific problems. Like for example, these kind of problems, when there is a graph, and if you want to build a quantum circuit for that and simulate that quantum circuit, there is an overhead associated with that, mapping, right? So you map a problem to a gate-based quantum computer that requires some kind of overhead. There are certain class of problems which can be directly mapped to analog Hamiltonian simulation without having to, go through that overhead of mapping the problem to these. So for certain class of problems, using these analog Hamiltonian simulations are much more efficient, right? Because you can just directly play with the atoms, interactions and proceed with the algorithm. So that is one advantage why these devices such as QAOA's Aquila may be very much useful, right? And then the idea is so there are advantages and disadvantages, of course. So this is quite hardware efficient for certain class of problems. This is more efficient than the gate-based problems. And here one can, work with any kind of geometry with the graph. However, for the gate-based problems, if you change the geometry, that might require, additional overhead. So did I answer your question in some capacity, Sarah?
Sort of, I guess. I don't know much about quantum, so basically I was like, what's the big picture? Explain like I'm 5.
Right.
I don't understand when you're like 1 and 2D geometries, like that means literally nothing to me.
Yeah, okay. So the take-home point here is that there are certain class of problems for which the mapping to these kind of devices is much more efficient.
Yeah.
And so these devices are like very kind of niche devices. So analog Hamiltonian simulation devices is not universal. They are good for certain class of problems, but when they are good, they are better than other devices. If that makes sense.
Yeah.
Okay. So basically, I just wanted to give a flavor of if you're familiar with adiabatic approach to solving problems. So basically, what you do is there are two parameters, this omega and delta of these devices, and what you do is you slowly change these parameters from an initial value to a final value, and at the end you make measurement to to find out the final state, right? So basically you prepare the system in a ground state where all the atoms are in the ground state, and then you try to drive the parameters, like the parameter in such a way that atoms go from ground state to excited state, and at the end the idea is that any transition between qubits from going from ground state to excited state is like the qubits are going from 0 to 1, right? And at the end you can make measurement to find out what the state of the qubit finally is. So like for example, if you're looking at MIS and you want to find out the partition in such a way, like some of the vertices are in state 0 and the other vertices are corresponding to state 1, then you read the state of all the qubits, and that gives you basically a sample similar to what we look at the max-cut problem, right? So basically the idea is that you switch on the device with some parameter omega, then you change the interaction between these multiple various atoms, and at the end you switch off and make measurement, right? And the idea is that when you make measurement at the end, this state of these neutral atoms is what gives you the final sample that you're interested in. Okay, so so in the interest of time, I just wanted to like quickly introduce you to Aquila device, what it looks like, and I think that is all I have for now. Unless you have questions, I would definitely like to answer those.
So I've got a question about Aquila and also Aquila devices. So, it's not a full gate-based system. It's quite particular. And in Amazon Braket, if you posed an ill-posed problem to the device, does it tell you this is an ill-posed problem for that device? Or no?
Actually, that's a very good question. Let's go to and test that right away. So if you look at the quantum task, the very first circuit that we try to simulate, right, a Bell circuit, and if you run the Bell circuit in the local simulator, is there any question or some discussion going on? Okay, no problem. So in the local simulator, if I choose bracket AHS, right, and try to run this circuit up here, it gives you an error, right? Because right now we are using a simulator for analog Hamiltonian simulation to run a gate-based system, so which is clearly not compatible. So that gives an error, basically saying that it's an ill-posed problem. Does it answer your question?
Yes, it does. So, I mean, in this example, it's kind of obvious when it doesn't support gate-based programs. But if you have something that has a device that has natural gates that will not actually be able to solve the gates that you want to solve, does it complain as well? So you have photonic systems, you have superconducting systems, the actual gates, the actual circuits that they can solve. Especially for photonics ones, are not the complete set of, they're not like true ideal qubits that can have all gates operate on them. So does it complain in that context or no?
Yeah, you will get an error that these gates are not compatible. But,
okay.
What Amazon Braket does is that if you provide a quantum circuit, it transforms the circuit into terms of the native gates, so that
So then the error is more on the back end side, right? So the idea is that you would it would do the translation, and then the underlayer, the back end, would complain saying, I don't have any natural gates that can generate. You're asking for something I can't generate. Okay.
Right. Okay, so I mean, I understand that like for the second session about QAOA and AHS, it was, especially for AHS, it was quite quick. So we can schedule another talk sometime later where I devote time to these advanced topics such as analog Hamiltonian simulation, go more into detail and show you how exactly this works, and that will give you a better flavor of how the advantages and disadvantages of these devices. So with that, I would like to thank you for your attention, and I have just one small request, and that is to, I have a survey up here. Basically, the survey, it asks you, basic questions about what did you find interesting and not interesting about this talk. So the link is up here, and I would encourage you to give your brutally honest feedback because that helps us, improve these kind of workshops for future iterations. And let's say if we have a second part of this talk, I would take your feedback into account and make this better for you next time. With that, I would like to thank you for your attention.
All right, thank you so much, Brajesh. I think that was a great session introduction, and thanks to Michael and Albert as well for supporting the chat. Michael, I think I'll use your coin flip analogy a bit when we talk about quantum. Thank you all for joining, and please complete the survey as Brajesh said. Hopefully we will see you all in another session. Okay,
yeah,
we've got a question. Yeah, Alex has asked whether you can provide the Git repo link.
Git repo link, it's quite easy to find. On Braket.
Sorry, Brajesh, did you have anything else to add?
Yeah, I just wanted to say that I would also send you the survey link. You can send it to the participants. Yeah.
Yes.
So
yes,
this
we
is
can
the
do that.
Amazon Braket Python SDK. Oh, Michael beat me to it. So it's there.
Yeah, and I'll just add, I've been posting links to our blog post throughout. I think what I've shown you is maybe not even 5% of the content that's on our blog post. So I encourage you to kind of explore some of the articles that are listed throughout. There's industrial examples, there's like scientific examples, there's all sorts of features on there. So that blog post is our primary channel for kind of showcasing a lot of the features of Braket and talking about customer stories and what people do. So there's a pile of content there. I encourage you to go look at it.
Great, thank you for that. Yeah, I saw all those links posted. Thank you. All right, so that means we can give you back 10 minutes of your time. And like I said, we'll hopefully see. Keep an eye out on Pawsey's event page. There's a lot of workshops coming up. Please sign up, register for upcoming events. Thank you all for joining.
Thank you.
Thanks very much.